Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
And we were just wrestling the mic from each other, trying to get, like, stop, we got to hit record.
Yeah, right. We hit a subject that we find some differences in how we view it a little bit. And I feel those are probably the most interesting for the listeners when there's some different perceptions of, what we can do and how it should be done. And,
all right. Well, we need to wind back a little bit. So
okay.
What started was you noticed in our listing of titles and stuff that's been published, a
right.
listing of failure mechanisms.
Right.
And I've talked to Phil about it. I think I talked to, who else did I talk to? Somebody else, Diana maybe. But it started with a question that came in saying, is there a repository or a listing of failure mechanisms? And they were specifically interested in plastic enclosures for electronics and the electronics type stuff. And the short answer to him was, no, not really. There's material science books, there's electronics books, there's, textbooks, but it's all not really, I think, what you're looking for, the way they described it. So I started thinking about that.
Okay.
And so that's what brought up this discussion. But you had a reaction to just the idea of listing failure mechanisms.
Well, because I believe that that's kind of what occurs in experienced reliability engineer's mind after they've been exposed to a lot of actual failure mechanisms and failures in the field and have done the proper failure analysis to see what the mechanical or the physical mechanism, the chemical mechanism that caused this chain of events to lead to a failure of the system. Okay, once you've done that, and you have some exposure, and you can get this from conferences too, when you go and see somebody talk rarely about a failure that they've had. It's very rare.
No, I found that going to the conference and talking to them over a mug of beer, you got more details about interesting failure mechanisms. Yeah,
exactly. Not at the public presentations.
Not often, no. You're right.
Because you can't disclose a lot of stuff because you've got it approved by the legal team what you can present, and that's very limited. Yeah. So anyway, but we have common ones. We're cracking of the solders. And things come about that weren't real common, like tin whiskers that happened way back in the 50s or something, and then it reoccurred when we switched to lead-free solders, and it wasn't, so it comes and goes, and as our technology changes and the packaging dimensions change, from going from the flip chip to direct application of the integrated circuit, the silicon onto the printed circuit material or whatever. It's now very, the mechanisms have changed somewhat. And we look at all the supply chains for all these things. Just go into iPhone, for instance. You've got the encapsulation materials. You've got the
flame retardant within the encapsulants.
Right. And at any level of that supply chain to each one of those component suppliers, anyone, like the encapsulant, the guy that makes the epoxy, ships it to the chip integrator in encapsulation, they could have a problem, and they have, as we experience. Some of us know that they have a problem with the TCE, the thermal coefficient of expansion, matching the lead frame or whatever. They have very proprietary formulas to make those as compatible as possible with the actual mechanical structure of the chip, the lead frames, and all that. And some of that might be disappearing as we, get denser and denser electronics. These things change. So I guess a understanding of the basic mechanisms of physics and cracking.
Well, I'm just thinking, like you're talking about cracking. There, you can get corrosion can lead to cracking, or crazing is another.
It can,
right? But also just
with that expansion and contraction,
expansion and contraction, heating, cooling,
right?
Or it could be motion that is, you would load it and unload it, and that creates work hardening in some materials.
Right.
It creates cracks. So the idea is that if you see a crack,
Yes,
it could have a dozen different, mechanisms that are at play. And then, so the idea of creating a list, it's not a list of every specific failure mechanism for every specific material, because as a handful of people, including yourself before we hit record, said, you'll never be done listing stuff. It's just a list. And getting photos of all of them and everything else would be virtually impossible. But the thought is, and the more I wrestle with this idea and trying to answer this person's question, was, well, we need, like I saw something on LinkedIn just the other day, and it said, here are 6 types of corrosion. And it had galvanic corrosion, and it had oxidation, and it had UV radiation, types of breakdown of polymer. And it had it said corrosion's like the top level one. And then there's all these different kinds of corrosion. And then underneath those mechanisms, then it depends on the material that you're actually on. Copper and steel both have corrosion. One protects itself and one eats itself. Keeps on going.
Right.
And
silicon oxide.
Right. But the idea is to create a I don't know, glossary, listing, lexicon is the term I'm using, is saying, well, there's corrosion, well, there's types of corrosion, and here's what those types are. And then here's some specifics underneath those things. And what you were leading with is that came about. I know about all these things because I've run into them over the years, and I've been fascinated with how things fail for, it's one of those odd things about what we do as reliability people. It's like, how's things fail? So I've learned a lot, but the idea, and it combines with the site and kind of the idea of this podcast, is, well, why can't we create a spot that helps people become aware of the range of way things fail, make them never want to get on an airplane again. And then, and so that as you see an issue, you have a better toolkit or awareness of what it could be. And then maybe shorten that time for actually sorting out what happens. But I totally agree with you, Kirk, is that when you're confronted with a problem, you still need to figure out what actually happened. What is the physics, chemistry, whatever? What are the details of that? And it will be unique in many cases.
And in fact, you just listed, just corrosion itself.
Yeah.
But you talked about all the compounding factors that could add. And it's not just, it's temperature, it's moisture, it could be chemical contamination, residue left on. There's just, and these are combined together and cracking.
Oh, what's the really pretty one? We got to lead off with that. Maybe make that the cover of the book. Is the dendritic growth? Where it builds a little tree of beautiful colors across your circuit board. Not a good look for your board.
No, like a tin whisker. It's kind of pretty. It stands out. It's a little spike.
Little spiky thing.
Spiky growing.
You don't want little silver or tinish hedgehogs across your board. That's not a good thing. Yeah,
especially as the densities get tighter and tighter, and that gap between traces and line widths is very, very small. So all that changes as the dimensions of the chips and density of the electronics change, then the interactions, the mechanisms all start to change too. So I think in general, you would advise anybody going into reliability, one of the basics that they might start studying is material science and the materials used in, especially metals,
polymers,
fatigue, learning, the physics of that, but not to really worry about, again, I focus on the fact that most of the problems that engineers in a product development and launch are going to deal with aren't going to be the problems five years from then. They're going to be the problems of the next production.
Well, I
usually
it's the new stuff that engineers don't have a lot of experience with. So part of the idea is that here's these different classes of problems.
Right.
And for example, if you're going into an environment that has a really big temperature swing from when it's overnight, like solar, right? It's quiet overnight, it's ambient temperature, and then it heats up And then once it becomes active, it heats up some more. So it gets a bigger swing than ambient, and it does it every day. And so
it's outdoor.
And it's outdoors, and there's all these other factors. But the idea is that, so we come up with a new material for solar collection and protection of that thing. If that designer isn't paying attention to thermal expansion issues, it's just going to break. It's just going to come apart. So part of the listing and being aware of the types of failures and the stresses that apply to them is to assist in design, in forming design teams, so that you're cautious of these things, conscious of these things.
Right.
And most of them intuitively are. They think through. The vast majority of design teams I've worked with are conscious of it. Now, back to the other thing is that the problems aren't always the ones that, are new. It's not. When I was at Hewlett-Packard, we had an issue with ceramic capacitors cracking. And I went to Dick Moss, who is the quality director, and asked him about it. And he goes, "Oh yeah, it happens every 5 years." He's like clockwork. Is our design teams forget that they're just little pieces of glass. And I said, "Why is that?" And he says, "Well, it's a commodity part. They use them all over the place. We use a lot of them. And after each disaster, we reinforce in our training and awareness that they're fragile. So be aware of that." But every 5 years, the new designers right out of school, not familiar with all the ways these components can fail, and capacitors are just capacitors, and they put them too close to screws, or they put them on a part of a board that bends, or, whatever. And he says, yeah, it's like every 5 years. And that I found I'm drawing a blank on the book, Design Paradigms by Henry Petrosky. He talks about this phenomena where the first designer with the new material or the new idea over-designs it. They have a reputation to protect. They don't want it to fail. They have a lot of unknowns, so they bulk it up, right?
Yeah.
And they do extra. But they teach the next level folks, and some of that cautiousness goes in there. But now we want to make it lighter, cheaper, longer, faster, whatever. And we start pushing those boundaries. The third generation of engineers working on that novel new concept, like not the 2 nanometer stuff we're seeing in circuits now, but the old style, I don't know, what was it, 20 nanometer size? I don't know how big they were way back when.
1 micron when I was working at semiconductors.
Yeah, there you go. So, but the designers of those, they're doing that for exercises in college, and they come to the field and they've never seen these things fail, and they push them and use them in different ways that get through some of those boundaries. And that's what's led many different things happen on a cycle like that, as we treat it as a commodity and forget that, hey, it's just a piece of glass. It can break, kind of thing. So
we have solutions for that. I
mean,
we
do. We have guidelines and reviews, but you have to be aware of that stuff. And that's where I think this listing idea might be a good idea.
Okay, I think that those are kind of the CAD systems. All those things need to be part of the design review, and of course with the CAD and the automation we have, and the higher level, and which is constantly kind of exponentially developing, because CAD systems build better CAD systems, and that's it's kind of the on that. But
I have a hard time with that. I have a hard time with that approach. If you're not aware of what that button over there does, it says age this material or flex it 100 times and see where the stress concentration is.
Right.
If you're not aware that is a potential piece that you need to take care of, the designer's trying to get the design done, and here's this material that we've used forever, and they put a radius on it and go, well, that's not quite enough. When we change that, make it a different radius. And now they break a rule. Yeah. Right. Yet I don't think we can put all the rules. We can put many in. I think there's keep outs, and there's, load simulations, all kinds of cool things.
There's a lot of design rules, right? A lot of design rules that need to be followed.
If they're used.
Well, they should.
Used. They're not always.
They're not always used. There's trade-offs in all those too. On real estate, solder, how placement, things like that. Okay, so there's always in fact, all of engineering is a trade-off, really.
Right. It is.
So looking at this, first of all, do you need that chip capacitor? Do you need those kind of things? Reduce as much as you can, but
Yep.
but at the same time, even the best, the chip manufacturer himself, yeah, he's got a whole bunch of, like I talk about there's a big huge stack, and the guys providing the raw materials to the chip, MLCCs, multi-level chip capacitors.
Yep. Multi-layer ceramic capacitors. Yeah.
So, multi-layer ceramic capacitor. Each one of those guys could have a problem in the mix of the ceramics, and it's basically a little ceramic spacer and metal between metal layers between two pieces of ceramic. And so it's a very simple, incredibly simple device. But yeah, at the ends, we have had problems with tombstoning, cracking, things like that.
Even corrosion going across it,
right,
if it's contaminated.
And then we changed from leaded, which we knew a lot about, lead solder, to a lead-free solder, which we didn't know a lot about. And they were all, doing different mixtures of silver. What is it? Silver. Sometimes copper. I think they've added that. And
well, there's SAC.
There's SACs.
Yeah, it's not silver. It's tin. I want to say, I'm drawing a blank what the A is. Acrimony or something like that, but that's probably not the right word. Some metals guy is going to roll over in his grave on me right now. And copper.
Yeah, and then Tin Whiskers came about, and we go, this a new thing that was an old thing came about again.
Well, it was one of those things that was. I remember those days when I was working on it on the new solder systems, and one of the big learning thing we had to go through all of our people on the plants when they switched over from lead to no lead, or lead free, was if it's bright and shiny, it's bad now. Whereas the leaded solder, if it was bright and shiny, it was good. It was kind of a quick visual cue.
Right.
And it changed all of that. So all these people I was in a factory, and they were touching up all of these joints, which cuts their effectiveness and causes like twice as many problems is just leave it alone.
Right.
Because they weren't bright. And so they were resoldering every joint on this thing. And it was like, oh my God, these things won't last a day. And because they made a bunch of cold joints and they made a bunch of other stuff. I'm like, all right, it's a different metal. It behaves different. Be aware of this.
And it has a different reflow temperature. And that was another problem that the people were using, they were doing kind of mixed lead, sometimes lead and then lead free. And, they would adjust the reflow.
Oh,
God,
and,
and I even saw, we have pictures of solder not reflowing because they had 183 was the leaded reflow temperature, and 205 or
sometimes 220.
Sometimes well over that for the lead free. And so, that led to poor solder joints, problems with that. So,
Well, there's a whole category of the learning curve stuff, the stuff that we need, that we just don't know we don't know as we use a new material or new process or whatever, in where the old process just doesn't work. And then there's a whole category of material variation. Like that's the most common thing I've seen from vendors is, if I get a material and it's supposed to have this tensile strength, but if I pick from the bottom of the batch, the stuff made on Tuesday, well, that's got like twice the tensile strength, and the bottom stuff on the Friday afternoons, like not anywhere close to that tensile strength. And so it's,
or one of the big disasters was, the electrolyte mix in an aluminum electrolytic capacitor.
They just forgot a component.
Well, they forgot a component, or they didn't know, or they weren't aware of it. And that was a very tough mechanism. You couldn't find it. Well,
you could find it. A chemical analysis.
You could find it once you did a chemical analysis, but realizing that the effect of that in the life of the capacitor, because the capacitor still would operate for several months, not years anymore, but so normally under several months. And it was, again, through stress that I could show in an hour, you could blow those things, get them to expand, whereas a normal capacitor, you could.
I love when I learned it. It says, what are those little crosshairs on the top of an electrolytic capacitor for? And well, that's the vent, and that's for when it's venting. And as it's venting, you're purposely trying to expel some gas. Oh no, it's not like a relief valve. It's just
Not
it's controlling which direction it explodes. Oh, okay.
And we saw a few of those. Yeah,
Yeah.
you could actually see where it opened up the can.
And then there's corrosive electrolyte all over the place.
Right, but that was a problem. That was an error in the
Design.
formulation.
Yeah, the
well,
design of
of
that
that,
capacitor.
right? Or in manufacturing, who knows if somebody left the right, cup of phosphorus in there or something, whatever. It's just and any good design can become a bad design by the failure of manufacturing, failure of the process. Like I said, with the reflow of temperature, it didn't have anything to do with the design. It had to do with somebody setting the manufacturing parameters and correct machinery settings for that. And that happens all the time. So those kind of things.
I don't know that we disagree a whole lot on this. There's so much to be aware of. And I think the idea of listing it, which caused the start of this conversation. And we just listed like 15 different mechanisms in 20 minutes, easy, and talked about them. And part of that in the episode and talking about failure mechanisms, I think you and I agree wholeheartedly in this, Kirk, is to increase the awareness of other people of what we learn, by experience, so that they can ramp up and learn about the next wave of weird stuff that's happening, and then they can teach us about it. But the idea of the listing is
that we haven't seen yet that are going to come into existence we didn't know about.
Oh, yeah.
And nobody knew about. It's a whack. It's always a whack-a-mole kind of thing.
Well, how many ways can a quantum computer fail? But the idea is that there's, just use. We came through a number of examples, but my hunch is, yes, it's a daunting task to create a listing of all mechanisms, but maybe I'll get somebody at Google to work on it because they want to organize all of information in the world. Maybe I could, but over the last couple of weeks, I've been doing a lot of searches and really am finding just bits and pieces. Somebody's a specialist at just these mechanisms and they talk about those. And there's another one that lists just broad swaths of stuff, so I'm still wrestling with the idea. So anyway.
It's, and it still goes against, it's the challenge there is that, again, we can't, and nobody really does, publish the actual case histories of a failure mechanism and its manifestation unless they're legally required to do so, or it's a court case. We just can't see that.
We got to put this in the show notes. There's a website I just ran into the other day, and Bob Latino told me about it. And there's a professor, material scientist in Brazil that has created a database, and it's got thousands of cases. Now they're all metals because that's what her specialty, her area of expertise is. But it's called Material Life, and it's amazing photos of the coolest stuff falling apart. And SEM photography. It's really into the details of cracking and crazing and stuff like that. And there are safeguards that you don't know exactly where this was used or whose vendor it is and all that other stuff. But it goes into details of like how things go from being a fine retaining pin to case hardened and cracked and finally fails. And it was I just had to rip myself away from it. So there are pieces and bits out there, but her site is just in great detail. And you know how material scientist people are. They love taking pictures.
Oh, yeah, I love it. I love seeing the actual photos and sims of the mechanisms and explanation. Now, you don't know how that was manifested or how it manifested the failure and things like that. And that's kind of the chain that is not, and how they found it, those kind of things. Anyway, go study your failures in your company. That's the way to learn.
That's the way to learn. Plus, we're going to try to help along the way as we can.
Okay,
All right, well, thanks, Kirk.
You bet, Fred.
Talk again soon.
Okay. Talk to you later.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.